For the introduction, Torricelli law derived from Bernoulli principle described the flux velocity of a fluid exiting an orifice under gravity, where g is the gravitational acceleration and h is the height of the fluid column. This experiment aims to validate Torricelli law by measuring the flux velocity of water at different heights and comparing experimental results with theoretical prediction. This study also explored the practical implant of fluid dynamics, including application in water reservoir dams and fluid systems while considering degradation caused by velocity, friction, and turbulence. By analyzing these factors, this experiment bridged the gap between theoretical method and real-world fluid behavior. The objective is to verify theorem's relationship by comparing measured and theoretical value of velocity. For the scope, insights from these studies are applied in designing water tanks, reservoir tanks, and fluid control systems. We have used 200 ml, 400 ml, 600 ml, and 800 ml volume of water. For theory and working principle, Torricelli law describes the parting speed of jet of water based on the distance below the surface at which the jet starts, assuming no air resistance velocity or other hindrance to the fluid flow. Every jet, even if no living horizontal, takes a parabolic path whose direction is the surface of the water. We also assume that it is ideal fluid, which means that the fluid is incomprehensibly non-viscous and laminar flow. Thus, flow cannot be integrated since same rule cannot be applied to non-fluid as their velocity and flow may not be same across the fluid itself. The speed calculate of fluid velocity out of an orifice under the force of gravity in a tank is proportional to the square root of the vertical distance between the fluid surface and the center of the orifice and the square root of twice the velocity caused by gravity near the surface of the Earth. In other words, the flux velocity of the fluid from the orifice is the same as it would have occurred by falling a height under gravity. Torricelli law can be demonstrated in this experiment, which is designed to show that in a liquid with an open surface, pressure increases with depth. It consists of the tube with separate holes and an open surface. The holes are blocked when the tube is filled with water. When it is full, the hole is unblocked. The lower a jet is on the tube, the more powerful it is. The fluid exit velocity is greater further down the tube, ignoring velocity of other losers. If the nozzle point vertically upward, when each jet will reach the height of the surface of the fluid in the container.
Hello. So what is experimental method that we use in the program? So first we have the clay marker. Second we have a cylindrical cylinder. Third we have the measuring tape. And fourth we have the plate to where the water must go when the hood of the cylindrical is open. And next the stand of it, the different depth. That's 30 centimeter, 50 and 70. The first thing first we need to measure the distance between the holes. Then we have to count the intersected depth of the hood in cylindrical tank. Then we have to fill up the cylindrical tank with bits of water. The most important is the measuring tape to measure the depth. When removing the excess clay from the hood is critical. water to displace from the three hole meter using the provide schema. Also, mark the horizontal distance of water including the remaining water. Then, measure the length of the water displaced that you want to displace water by using the measuring tape. Next, let the water from the cylindrical tank to flow out completely. Make sure there is no more flow out from the drill hole and record the time. Repeat the same step for 0.15 meter for 3 times to get the average horizontal water displacement length (m). Then take the reading of head of water level and the horizontal displacement and record it in the table. Repeat the experiment with the different head of the water level. Repeat the same step for 0.15 for 3 times to get the average horizontal water displacement length.
Next, this is our result for this experiment. We use the height of cylinder placement from the ground is 0.3, 0.5, and 0.7. And from the data, we calculate the velocity theoretical, the experimental velocity, and the percentage error.
For the discussion part, first explain your selection on dependent, independent, and constant variable. The dependent variable for the experiment is the maximum water trajectory distance from the orifice of the tube and the velocity of the water stream. The independent variable is the head of the water level in the cylindrical tank with ground level as reference because the head of water level can be different during the experiment by filling in different volume of water. The constant variable is the viscosity and the density of fluid used throughout the experiment, and we use water as our source of fluid. For the second question, clarify on how you can relate the Bernoulli equation with the Torricelli law for this case. Show all the derivation and explain each step. Torricelli law may be derived from Bernoulli principle and relate the velocity of fluid leaving an orifice in a fluid container to the head of the fluid above the orifice. Torricelli law is derived from Bernoulli equation by equating the potential energy in the static head of liquid to the kinetic energy of the water leaving through the orifice as follows. P1 over rho g plus V1 square over 2g plus Z1 equal to P2 over rho g plus V2 square over 2g plus Z2. The P1 and P2 is zero since it is atmospheric pressure. Velocity at the point 1 is considered zero because it has no movement of fluid, is so small and almost to zero. Z2 is zero because we take that point as a datum. Subsequently, rearranging for the velocity, we have Torricelli law, which is v equal to square root 2gz. Question 3 is asked about percentage of relative error for the theoretical and measure experiment. So this is our percentage error that we get from the result. The last question is source of error and method to minimize the error. First, source of error. Starting and stopping a stopwatch can be various from different which can be potentially cause correct time taking. Releasing of finger from the hole can be potentially cause inaccurate time taking. For the method of minimize the error, obtain more accurate result by calculating average value. This can be obtained by repeating the experiment several times. For the source of error, parallax error due to observed eyes being positioned at an angle to the measure marking when taking measure to calculate the H1, H2, and H3 measure for the maximum distance the water projectile. For the method of minimize the error, observed eyes should be parallel to the scale. And lastly, leakage occur when covering the hole in the cylindrical tank hole is not covered properly. For the minimize the error, use a tape or stopper to more secure.
So our procedure is tie back long hair and avoid wearing loose clothing and jewelry that could cause in equipment. Use the stir when fill the water in cylinder when the head of y-axis of blade at 50 centimeter and 70 centimeter. Make sure the eye is perpendicular when reading the scale of tape meter to avoid parallax error. So for conclusion, the experiment successfully verified Torricelli law, demonstrated that the efflux velocity of water from reservoir is proportional to the square root of the head of the fluid column above the exit point. The experimental result closely aligned with the theoretical prediction, which minor the responsive likely due to frictional flows, measurement error, and turbulence at the orifice. Overall, the findings validate the relationship and the trend observed in the velocity versus head graph confirm that as the expected square root dependence. This experiment highlights the practical application of celestial law in engineering such as designing water tank, spillway, and the other fluid flow systems. Future improvement could include more precise timing method, the use of more continuous orifice, accounting for viscosity and surface tension to minimize experimental error.